So when you install the pipeline for Gravity, you have the option to also download demo data, which has been taken for this purpose to play with. It's public data. It's in this case a data set from XCTEL, which is a resolved star, and it has a size about of 3.7 gigabytes when you download the pipeline. So you not only the pipeline will use space, of course, but the demo data set will use about this amount of space. When you download this via the official ISO download script, they end up in a folder called, and this is what I wanted to show you, user share ISO pipes data demo Gravity, and another Gravity demo Reflex 0.7. And this is the directory structure. So there's a folder called calibrator, then dark, master P2VM, P2VM science, and vis uncal. These are the files. And so we will just have a brief look at what's in there. For this purpose, you can use a just looking at notes here, dfits command. You may know dfits probably because it's a very old but well-known tool which basically looks at fits headers of files and then extracts the value of certain keywords and then displays them. And in this case, we get a nice overview of what we have in this directory. We have a, under calibrator, we have the calibrator observations for the star. So here you see, in fact, I should, so this, as far as I know, is very hard to read for you, if I remember correctly. So what I'm going to do is to create a magnifying lens, which is here. And you can see here, the first 6 files are files from the calibrator, HD184349. This is the observing name, which shows you a little bit about what stations were used, A0, G1, J2, K0, in high resolution mode, split polarimetry. There's a standard. This means it's a calibrate observation in the sky and the standard. And the same thing again. It's 2 object sky object sequences in the medium spectrum resolution. And here you see also DITs and other informations. So then we have further down a calibration file here, a dark. Then let's skip these files called master P2VM for the moment. Then we have P2VM. This is a so-called pixel to visibility map. This is a calibration file which is taken with an internal light source to basically provide a means of converting the measured pixel values on the science frames into visibilities. And they have a certain number of files. I think it's like 10. And they consist of a dark, some flats, wave calibrations, and then the actual P2VM files themselves. And these columns for DIT and other things is just for showing them. Basically, what you will see here is that these files belong together also if they have the same detector settings. Otherwise, they wouldn't match really. So then at the bottom, we have now actually the science observations. Here it's under the folder science. There are 3 files, an object sky object sequence. And what you see here, in the same settings as the calibrator. And so then there are 2 other directories which I have not further explained. This is master P2VM and vis uncal. So you might have used the ISO archive already. When you download data, And there is this one step where you were asked whether you just want the raw files or whether you also want to have the master calibrations or processed calibrations, as they're called. And if you choose to also get the processed calibrations, which are here called master calibrations, you get those additional files. And I will show you in the workflows, there's a workflow which uses those and which is much faster in execution because it doesn't need, you don't need to reduce the calibrator observations again. And the additional advantage is that our QC department has also verified those calibrations. So that also, so these are just the master P2VM. And then the calibrator observations are also officially calibrator observations, which are processed by the quality control department. And they put these observations in this folder called vis uncal. Uncal just means it's an uncalibrated observation, a reduced data set for the calibrator, for the target, science target, and the calibrator. Okay. Anyway, so this is the structure for these files. And now let's start the Reflex workflow. So I have here I'm here in the home folder in a directory called Reflex data, and you will see why that is. So I call ISO Reflex. This is the command basically which is set up when you download the pipeline to call the gravity pipeline. So this again is a fairly small window. I won't magnify it for now because we only need to click here on the left under File, Open, and then you get workflows. You see I have several other workflows installed. We are interested in the latest gravity workflow. This is 140. And you see there are 3 recipes. And maybe it's time to get a little magnifying lens here. Gravity master calip, gravity viscal, and gravity underscore WKF for workflow, basically. So the workflow WKF basically does everything to reduce the data, but not calibrate it. So when the data are reduced, then you can calibrate them with the viscal workflow. And a small modification for the gravity WKF workflow is the master calip workflow. It also starts with the raw, as I described before, with the raw science data, but with the master calibrations for P2VM and the calibrator stars. We won't use that workflow today because it's just a shortcut. And if you're in a hurry and you don't have much disk space, you can use that. And we will use gravity WKF, and we open it. And let's get rid of the magnifying glass. So here it is. This is again very small, but Reflex has a nice feature which you can use the little wheel in the mouse to magnify it if you just rotate it. And now you see it's moving out of the screen, but this is no concern because you click here in the upper left, there's this button with these arrows, and then it fits it right there in again. So we can also shift the workflow canvas a little bit up and down. I don't know, for those of you who have never seen this, might be a little bit confusing. Basically, the steps in the reduction are displayed here visually, basically from a step 1 where the data are organized, matched with the calibrations, and then they have these lines connecting various recipes, reducing certain file types, combining file types, and then in the end renaming the files appropriately and saving them. Okay. And then above here, we have certain instructions, and especially the setup directories is the one which you have to look at now. And when you download the demo data, they're basically set to values where you can start the workflow right away. and it will, without modification, it will find exactly where the data are because they're put into those default folders. Now this folder for the demo data is a little bit unfortunate in the sense that it puts it in user share, which not always accessible if you're not a super user. But anyway, this is another issue. Um, so as I showed you, we have those data in this folder called raw data dir. I can make it a little bit bigger. This is correct. And the root data dir is basically the directory where all the results will be saved. So this is basically the default is the home directory and then a folder called Reflex data. Okay. So these two locations are the only ones you might want to modify for yourself. You can just double click on them and then you enter a new directory if you want to. Okay, the calib data there is something you should not change. This is just a system directory for the Gravity workflow. We will have a look at this later on because it has one important file, which is the JSDC calibrator catalog. Okay, and then the output is stored again under the root directory in Reflex end products. Okay, and also this folder will contain other folders called Reflex bookkeeping, temporary products, and logs. Okay, and we will have a look at those later because some of them have really important information in them. So we have here on the right we have some global parameters. Which I will not go into detail for all. One thing is convenient here for my purposes is a FITS viewer, and I want to edit. We're using the FITS FV for the FITS viewer, except that I have this located somewhere else, so that I want to put that in there. Let me look. Here it is. I have it under user local source FITSView 5.4 FV. So I just put that here. It comes in quite handy if you look at the results. There's also global plot interactivity, which is interesting at the later step. When we calibrate the data, it is set to true and it will ask the workflow to display some results visually. And in some cases, you can even, for some workflows, you can even change viewings and something like this. I think for Gravity, it's not possible, but the Matisse workflow allows you to do that. Okay, so these changes have been taken over right away. And before we continue, I want to mention to you that you can, if you made a lot of, well, if you made a lot of changes, actually we're doing perhaps one or two changes down here later, you can save this workflow, except it's here called not save as, but export as. Don't ask me why. You can export it as an XML file. This is you can rename it into something like for example, my workflow. Okay, here in this case it doesn't work because I have no write permission to this area. So you would have to enter a full path to a directory which you have control over. And then you can then you see it in the list when you have done that. It would show up with your name, with a given name here, and that is very helpful if you made a lot of changes. So when we look at the recipes down here, there are basically two important ones. One is the Gravity P2VM, and this is a step which is the one which takes longest. And then we have Gravity Science. So I would, in the interest of speed, I think we should start this workflow because it will just take a little while. We animate it because we want to see in which step it is. And let me just show you one more thing. To modify settings of parameters, you have to first open the actor because these actors are not basically atomic actors, but they are combined, composite actors. Some simple ones you can open directly, like the data organizer, but here you have to first open it, and you see it's already a composite of some other actors, and now we have the gravity vis actor, and that's the one, that's the designation you find in the pipeline manual. So here you click on configure, and then you get this huge list of parameters you can modify, and um, and I think what we will do is we just start the workflow and then open a second window while this is running, and then explain this further to you. Okay, so I click here the play button, and so we see here three data sets. Again, this is a bit small, so let's get up the magnifying glass. You see the calibrator, the science target, the calibrator. For now, we just do the first calibrator, okay? Because otherwise it might take too long. And I just get out of this lens here, and I play. Ah, wait. There might be something interesting to see here. Right. These are the files it will take to reduce these data, and so let's look at them a little bit in detail. So there are these three files: object, sky, object, or sky, yeah, object, sky, object. There are these ones. And you see when you click on it, you see a little bit of a FITS header here to the right. You can widen this to see more of it. Scroll down. Can be useful, this feature. Then a calibration file from the static calibrations, this as well. Then we have our dark for the P2VM, and then we have also the P2VM. And there are all these dependencies, you see very nicely. The P2VM depends on the dark, which was taken for the P2VM, and so on. It's not the same dark as for the science because the DIT will be different. Um, so now we click continue now after we have looked at this. And let's turn off the... so I just say continue, and then it works. Okay, so now it's in gravity dark. This is a very quick step, and then it will proceed to gravity P2VM. Okay, so we can... the gravity workflow used to be pretty resource heavy, but this is no longer the case. We can briefly look at our system monitor and the memory. Right now, 3.3 memory gigabyte allocated, and it will go up to about 5 gigabytes. So it's not too bad. So my computer has 16, so it's plenty. Okay. Okay. So while this is running, we could look at these parameters here again. We can go to no wait, this is something else. Applications, file, open. We can just open the same thing again. Maybe move it somewhere else. The computer's a bit slower now in opening this. Feel free to ask questions in the meantime or in between. Or maybe it's just not doesn't want to open this while it is busy with the workflow, especially the same one. So we'll just do a different session here. So we do the same thing here again. Okay. And let's open the gravity science actor, gravity viz, configure. Okay. And Okay, so the interesting ones is, okay, there's one called P2VM reduced file is set to false, so it's not produced right now. If you have problems with your data, I used this once when I observed a target which was quite resolved, and there were 4 baselines tracking the fringe, which means that the other 2 had a very low signal. But if you have 4 baselines tracking the target, then the constraints are complete. So also the other baselines are constrained. But for some reason I got only 3 or something like this. So in this case, you can turn it to true, and then you get a file which can be visualized. I'll tell you later how to do this, which gives you all sorts of information about fringe drops, fringe signal to noise, baselines tracking, and things like that. So that can be very useful. Um, so going down, there is a so here's, for example, the vis correction. There's a correction for tracking performance and scatter using a certain method, which is described, or several methods which are described in the manual, and this can be set here to different values. A V factor is the standard, and should only be changed if you really know what you're doing. Then here's another nice thing. It's set to false by default, flat flux. I put it to true usually, and it basically calibrates the flux with the instrumental flux response. So it normalizes that basically, where the instrumental response comes from the measurement of the P2VM. So it means you still don't get, of course, the true object SED. As you know, as you may know, the gravity pipeline also produces spectra for every telescope in the output file. But at least you have removed already a big part, which is just merely instrumental response. So what you still have in there is, of course, the sky and the telescope. Okay, um, and so all these are described in the manual, basically. Okay. Um, so let me just take one other thing here. Yeah. Okay. So okay, and we already get some feedback now from the pipeline. Let me remove the. So here we have now a window called. Now this popped up here on our workspace here, even though it belongs here to this one. Geez, it is here. Okay, Product Explorer. So the pipeline finished the reduction of the first data set, and it always pops up this Explorer where you can look at the results. And you see here two calibrator files reduced, and you can actually inspect them. Oh, wait. Um, Inspect generic. And you see it pops up right away, the OI Fits Explorer, because that's what I put here in for the Fits viewer. And you have this, if you're familiar with OI Fits, this is similar to Fits, but it has all these binary extensions. And you can, there are two visibility and triple phase extensions also Flux, one for the fringe tracker and one for the science channel. So if I go here to OIVis 2 and go to plot, I can I can get a quick overview of what has been, of what the data look like. Now, this I just figured out a couple hours ago. You put element number in X, which is basically the coordinate axis which relates to the wavelength. And then in Y, you put the squared visibility and you plot that. And yeah, so you see pretty high visibilities here, some actually larger than 1.1. Uh, it's some calibration which still has to be applied. And this is from the calibrator, but you see 6 different baselines, okay? So you just click continue, and the workflow has finished, okay? And there are these little windows which show up on which files they are working, like this one, and then the left window, the one which has finished. So if you're reducing a lot of files, these windows are helpful in looking at the progress. But we don't need them right now. They're recreated every time, again and again, when we run this workflow. So now in the next step, we can now either look a little bit at the quality of the P2VM, but I think we'll just leave this for a little bit later, depending on how much time we have. Because if you have a problem with this calibration or with your data, then this is the first thing to check whether the P2VM was properly taken and reduced. Okay. So let's just reduce the remainder of the data sets. Let's scale this back to see the whole workflow. And now I click play again. And now what you see is you see the workflow properly realizes that, okay, one of the files is already reduced. We don't need to do this again, so it doesn't have a check mark, but the other ones have not. And we want to do both of those. So we let's see. Yeah, I think this is all what we can say here. The inspect highlighted for the files. This is something we have done before. So we can just tell it to continue with this work. And you see it skipped the P2VM right away. We're already in the science template, science recipe. And so we will not have to wait for too long for the last two files to be reduced. So maybe just to tell you a little bit more about Reflex, one very important, really nice feature is the data organizer, which is here to the lower left here, this the yellow box. And this is something which, if you have heard of Isorex, which is basically the engine at the bottom of this this chain of reduction, which actually crunches the data, um, allows you to associate the science files with the proper calibrations. Yeah, and this is not an easy task, because if you do it manually, you have to use the dfits command to look at all the important instrumental parameters to associate the science files with the correct calibrations. And the data organizer will do this automatically for you. Okay, so it's a very huge advantage of using Reflex. And then of course the other advantage is that you can do a crunch through a huge number of files in one go. You can just start it in the evening and come back home, come back to your office next morning, and everything is finished. Okay. But of course, if you are really into Isorex, um, Reflex has these directories. So we go in Reflex data because this is where we work. Oh, it's already done with this one file. Reflex data. And we go into Reflex bookkeeping. Okay, so there's now gravity here, and there's gravity. So it's gravity this which we ran here. Gravity like this one here, and then we go to latest, And here you see a log dir, for example, and data.sof. This is, for example, the set of files which was given to the Isorex recipe. But actually, even more helpful is not Reflex bookkeeping, but I think it's maybe called. Oops. No. We go up one level. Let's see, Reflex 10 products. So let's go into GravityViz. I was looking for the command file, but I can look for it later. I think it's under bookkeeping, but let me just check my notes. No, it should have been like that. Okay, anyway. So Product Explorer opened, we're done. All files reduced. Just continue. So now let's go to the calibration step for now, just to get finished. Let's close this here. So this workflow is done. I'll just minimize it. So we don't need a. So now we go back to File, Open, and now we go to Viscal and open this one. Okay. Okay, so looks very similar. Not as complicated because it has basically one recipe here. Visibility is calibration. Then there's again the setup directories and everything. We don't need to change anything for now because we're in this default directory tree for the demo data. And so we can run this right away. So here we see one data set, okay? Now don't worry because before I've talked about 3, but what we're talking about now is to calibrate the science target data set. That's why it's only displayed like this, because that's the only science observation we have. We have 2 calibrators before and after. So if you want to see where they are, you click on Inspect Highlighted. It's always good to click on this button to see what you have. So here you have these 3 observations actually now, cal, and then there's this thing here. This is the diameter catalog from JSTC and in this static calibration directory. Okay, and you should make sure it's a FITS file that your calibrator is in this catalog, because if it is not, the pipeline would not be able to find the diameter of the calibrator, and instead it would get the diameter of the calibrator from the OB definitions. For in Gravity, it's like this, that you can actually specify the calibrator diameter in the acquisition template. For Matisse, it's not like this. Don't ask me why, but this is the way it is. So so that is just a reminder that already at the definition stage of your observations, when you make the OBs, it's first of all it's good to select calibrators from the JSTC, but if you don't have them there, which can happen, then just make sure you put the best estimate for the diameter in your OB, so that you get a good calibration. If you don't do this, there are ways later to fix this, but they are a little bit more complicated because there's a lot of fiddling with the fit setters then. Okay. So we can just continue this here. And this should be fairly quick because it just has to do this correction for the diameter and then divide psi by cal. And this error message, I don't know where this comes from. We can ignore it. And there is this plot here, which, okay, is not terribly useful. It just tells you a little bit about what the visibilities are in the end. But let's just continue it because with our FITS viewer, we're in a much better situation to look at this. And if we look at this now in the product explorer and its dependencies, we see our science file has dependency on the science observation and 2 calibrator observations. Okay, and actually what we get here, they also as a transfer function here. This is the file TF transfer function. Then the actual calibrated visibility file is called like this, psi, the name of the target name you gave it, our instrument, baseline, configuration information, and psi vis calibrated.fits. Okay, so we can look at it again. We say inspect generic. If I click this, then I have to enter the path again. But I did this already before. Actually, maybe not in this workflow. I don't know. Oh, it is in there. So now we get the science target, okay, not the calibrator, of course. And we go down here again, we plot, we put the element number in X, we put the squared visibility in Y. And you see we have a nice resolved single star. The baselines are not directly labeled here, but there are 6 of them. And yeah, so this is quite nice. And actually, we don't want to quit the FITS viewer. We can look at the phase. So we look at, let's see, phase is in OIT3, so we do that. We do T3 phi, plot that. So despite being resolved, the phases are close to 0, so we were dealing with a single star. And also the triple amplitude is available. You might never have really heard about it, but it is also a very useful quantity in special cases. And you see again this pattern of resolved and less resolved triple amplitudes. Is a complex product of the 3 complex amplitudes in the triple product. Okay, so so this all looks quite nice. And we can click continue. And our workflow is finished, and we have calibrated visibility data. So let's see. So we have like 15 minutes left, or a little bit less. As I said, interrupt me if you have questions. Let's see. What I wanted to do is go a little bit into some details about tools which are available for the gravity data reduction. So this means we have to find our data product somewhere, and I have to open my notes. Okay. So, for example, we want to have a look at a log file, which gives us some feedback about the data quality. So we go into Reflex data, our main data product container, and so here, look at log files. So we go into Reflex logs. So you see the structure is always the same. The first is like the name of the gravity for the recipe. So we go into gravity, not gravity viscal, because that's the reduction step is the important thing here I wanted to look at. And then we go to gravity vis 1. And then for all reflex reductions, the directory tree always contains at this point a list of subdirectories which are just have the date when you executed the recipe. Okay, so this might be a little bit confusing, but means a lot of typing and so on. So this is our first execution. So there's one file in it called isorex.log. Oops, sorry. So we can look at this here. Actually, this is a calibrator, so it should be actually not have any problems. But there is something I wanted to look for, which is called let me just check here real quick in my this is a file. This is a PowerPoint which I'm going to upload at some point on the conference webpage. Okay, I'm looking for the string valid frames. So let's look for valid frames. Valid. Here we go. So here you see valid frames 100%. So perfect. Calibrate observation was fine. There might be some other messages in here. So this is really nice. Then the next folder, the next date we have is from our reduction of the other calibrator and the science target. We can again look at isorex log. So now, of course, I don't know which one was which. We have here 100%, 100%. There should be another section, yeah, down here. So one of them is a calibrator. One of the science, we have 99%. So if these values are significantly lower, then there was basically a problem, either with your target being very difficult, the weather not so good, or something else. So this is one thing to check a little bit. So then if you are Isorex aficionado, then you could go up, let's see, a couple levels, go up more, and we go down again into Reflex bookkeeping, Gravity Viz, go into latest. Yeah, this one has a file called commandline.shell and data.sof. For example, this is for anyone of you who has used Isorex. Probably maybe nobody. Data.sof. So this tells you, this is basically the set of files which went into the Gravity Viz recipe. And the data organizer did all of this for you. Otherwise, you would have had to do this manually. And then the command line, if you want to re-execute the recipe quickly with changing things manually, sorry, I'm mistyping here all the time. You can just run this shell script. It sets environment variables, and then here's the command, pretty long. And I know colleagues from Bonn, for example, who basically have their own scripts to just set up these command lines and set of files inputs and run it like this. And then they crunch a whole batch of files taken during the night like this. Okay, so that is quite useful. That Reflex leaves these intermediary products and scripts and everything also for you to use. Okay. So last thing I wanted to tell you about are these so-called Python tools from the consortium. It's very nice that they are providing these for the public. Let's just use the same folder we are using now. There's just a single command to execute, and this will also be in. It's on one of the slides, which I will upload. Using SVN, this is how they are organizing the work on these tools. You don't see Unfortunately, I have to magnify this maybe again for you. Let me just do this real quick. See, this is a commando I'm putting in there. As I said, it will be in there, SVN, and then there's an address to download these tools. Let me just hit return, and you see here's a lot of stuff showing up. And you can use these tools to we'll use entire nights at once. And what I'm interested in, and this is why I'm showing you, is are uh, are those which create visualizations of data quality. Okay, and so we will not use this downloaded set of commands now, but another one I have already done before. Or we could try it here also. So you can go now into a folder for the end products. Let's see where did it do this. So if we want to check the quality of the P2VM. So what we do is we go into Reflex data, Reflex temp products, Gravity P2VM, and this I'm going to cut and paste in here. And there is only this one folder, and then it has this fits file, and this is this file here, which is here. It's just called Gravi date and so on p2vm.fits. Very easy to remember. That's the reduced p2vm file here. Okay, and so what we want to do is we just run the the Python script called run gravivisual.py. Okay, and you can use this for all sorts of things, all sorts of files. It's always the same one, except it's written in Python 2.7, and my Linux box has 3.8 or so. So I'm going to the Bash shell, where I have Anaconda 2. So now it's Python 2, and all I need to do is I run. So where are we now? I could do home/reflex data/ Python tools run Gravi visual.py, and as input I take that file here, which was that thing here. So input this file. So now this goes to this file and makes a lot of nice plots and creates a PDF. So here's our PDF, and then let's look at the PDF. Oh no, I don't have to leave the bash shell again and look at this PDF. It's just called, okay, Gravit, the date and time, p2vm, p2vm.p2vf. And it looks like this, okay? So the first thing you see here, let me open the, it says quality control report, warning, some warning here. Okay, this is only yellow colored. We have seen this data set is okay. It's probably because some slight issues with photometry of, I'm not sure exactly, is it, these are all the basically the detector windows which are used. You have to read the Gravity user manual for this, where the data are recorded in the chips, and each area is investigated. And so maybe there was a little bit of issue with the coherence in the photometry. It's the first page which you basically have to look at, okay? And usually it looks green. If it's red, then you have a really problem. And then you should contact ISO, usd-help@iso.org, and let us know about a problem and ask for help. Okay, and so and this script can be run on anything. And so I did, for example, when I had reducing some of my data and had a problem with this, I looked at another file, which was which one was it? I think it was this one, PTVM reduced file. This is with this pipeline parameter for gravity viz for producing PTVM reduced raw data. This is basically raw data which is calibrated using the PTVM. So it has already the pixels converted to the visibilities, but it has not done any averaging. And here you can scroll down and see all sorts of really, hardcore, detailed message about global OPD signals and so on and so on. And so there is a page, go a little bit too far already. Here, this is an interesting, this is this rejection flags per baseline for the science detector. You see this one is actually quite nice. It's, I think, probably the calibrator. This is from our data set here. 0 means that the fringe tracking was perfect. And then 1 means there was a low signal to noise. And this is a very short observation here. So these are, I think, seconds. And then if you go to fringe tracker, it's a little bit above that, which is even more important because a fringe tracker has to work. A science target might be too faint or so, or problematic in the science channel, but the fringe tracker is, you see there's only 1 blip on 3 baselines. Maybe there were low signal to noise at that point, but so we have the other 3 working here. So if you see here lots of a low SNR or low state or both, then you can already tell that there was a problem with tracking fringes, which could explain problems which we have with the data. And then you could go into gravity viz and try to fiddle with the parameters related to this to push it a little bit and say, okay, you can accept also the low state SNR number 1, and then see whether you can get a little bit of signal to noise back for your science target. So I think we're more or less at the end. We looked at the, yeah, I think that's it. Let's see, is there anything else I could mention? Yeah, I think that's it. So thank you, and let me know if you have more questions. I hope you're all still awake.
Yes, thank you very much, Christian. And indeed, if anybody has a question, please do not hesitate to either raise your hand or put the question in the chat. Otherwise, you can always put the question later in the Gravity channel if you prefer. And as Christian said, he will put the presentation into the files on the channel, and so you can get access there as well. So you can also have a look, and you can then maybe also, if there is something unclear, do not hesitate to ask a question in the channel.
Yeah, the presentation is not complete. It was just a few slides which go along the way. I have here as a reminder of the presentation. But as Henri said, the presentation was recorded, so you can listen to it again, I assume, and then maybe this will then answer questions if it was just too quick at some point. I think I have some coming up here, or no?
So no questions?
There's a chat.
Well, I had my hand raised, but okay.
Yeah.
thank you very much for guiding us through ESO Reflex. So my question was, like, the workflow that you showed, it's I guess it's for a reasonably simple configuration where you just have a single star that you're trying to get the diameter from. But if you would have a different science case, for instance, you're looking at binaries or with slightly more separation, would this workflow change a lot? Would, like, in what respect would you have to change things to this example workflow to make it work for your own data set?
Basically nothing. That the idea is here that this workflow does not make any assumptions about what the target might look like. Basically, it looks at the fringe tracker data, and then, well, not really. It has a set procedure to reduce the data. Basically, I can't go into the details more. So it really does not depend on the target too much.
Okay, thanks.
I mean, if you have a heavily resolved target where you're basically only tracking with like only 2 or 3 stations, because on the other ones the target is too resolved, then indeed that there's a strong dependency on the target. But the fringe tracker has only 5 spectral channels or something like this, so the channels are very wide, and so the signal to noise is much higher and enables it to even track on the faintest of all signals.